Hello, fellow engineers, and welcome back to Factorio. My name is Nasty. If you've watched my channel for any amount of time, you will know that one of the number one things that I talk about quite often is the concept of inserter clocking. And we bring it up almost in every single video. It's a point that we focus on quite often, especially in the previous competition series that I've been hosting here on this channel. We talk about inserter clocking and figuring out all the different timing variables. We've evolved quite a bit from the lead follower days to now doing very precise tick by tick direct little or small inserter timings for when a value is supposed to do something. And we've gravitated now to the point where it is preferable to create these large indexes or specific ticks on and off ranges so that you can lock an assembly machine into a very specific discrete timing range. Well, that's great, but it is an absolute pain in the butt to go and generate any of these clocks and to figure out all the timings. Normally, the way that this would be done is that you wind up going and taking a build like this, and you go and very specifically say, okay, from these ticks, this is when I want this chemical science to come out. I want it to do it in 2 swings back to back like this. And then what you would normally do is observe all of the inserter inputs that are coming in and then record, okay, what's the clock currently? What are the tick ranges? I've talked about in the past how you figure out the full cycle duration, how many cycles you're going to need, what the total duration is to get the least common multiple of all the input ingredients. Okay. This is all really complex, and doing things over and over and over again seems like something that we should automate. I will tell you that I've been working on a solution to automatically generate these clocks. So I'm a programmer, I'm extremely lazy. I hate going and doing something a second time, let alone 100 times, and trying to figure out all the clocks that you need. So what I'll tell you is I've built a program, and every single clock that you see in this particular layout that I have here has all been automatically generated with the program that I have built. So if you find that interesting and want to know more about that, stick around. I'm going to go and demo exactly how this program works now. Let's say, for example, I have a build like this, where I want to go and produce 240 bricks per second out of these 3 furnaces. I know this is going to have enough speed per second to go and craft the amount that I need. It's 129 per second, but I want to evenly distribute the load across all 3 of these and have all the inserters exactly timed when they need to output the items. Ideally, I know I want to do this in 6 swings to maximize the amount of times that these inserters are going to actually swing and then stop again. And ideally as well, what I would like to have happen in this very simple case is I'd like all of the inputs to be exactly synchronized. You can see here, this is 63, 63, 58, 58, 63, and so forth. And I want all of them to be exactly synchronized when they start and they stop. Since they overproduce, we know that we are occasionally going to stop at the end of a cycle and have them at 100 completely. And then we want the inserters to pull the items out. And we only want to do it when they're at that phase to prevent them from picking up in less than a full stack size of 16. So you're seeing here that it's always grabbing 16 and unloading 4 at a time onto the belt. So that's the ideal scenario that we would like to have. So in that scenario, let me introduce you to the automatic clock generator that I've created. So this is a web app that I have created. You can see that here. This is a web application that specifically its job and what it does is you can go and customize and set up all the parameters that you wind up needing to describe your build. In this, in our case, we have a machine here that's crafting stone bricks. We have 3 copies of that, right? So we have 3 of those machines. Let's go and I'll open up Factorio in the background so we can showcase both of them. So in this scenario here, we're going to have a configuration where we're going to have here 3 assembly machines. So that's why we're going to have those 3 copies that you see up there. And we want to produce a target rate of 120 items per second. That is the current goal. So that's what I've inputted on the top. And I've also selected the target output recipe. And so you can see here, I have the ability to select any recipe that's in the game, and you can select even modded like items that exist. So if you have a modded playthrough, you could technically go and just upload the dump from Factorio, and we could update this to run. This is only running locally in the browser. I don't have this hosted anywhere. This is more of a proof of concept and a demo showcase for this. So just keep that in mind as we are talking about that. So this is something that only currently runs locally. So there are some other things that we wind up needing in order to compute this. You see a couple properties that are in here. So you have the recipe for the machine. You can add as many machines as you want. You can select whatever their recipe is. But the idea is to go and create all the inputs that you're going to need, along with the inserters and what they're picking up from and what they're dropping to. So we've specified in here that we have a belt, which is a turbo transport belt. That's this guy over here on the right. We have then 2 lanes they're going to be occupying, which is stone bricks. This is just going to be an output belt, just for a very simple example here. We have filters that we have pre-selected in this example. If you don't select it, it automatically figures out what the machine is going to be outputting and then just displays that here. So we don't need to actually configure it, but I have shown that you can actually go and filter any of the items that you want from these individual machines. Now, the next thing that we do is the productivity amount. Well, there's 50% productivity. See that on the right-hand side there. So we've inputted that amount. Now you see this really large decimal number. So where is that coming from? Because when you hover over the right-hand side, you see the crafting speed is just 91.9. Well, you could use that, but there's technically rounding errors in the way that we actually calculate this. So there's a very simple command that you can run to get the crafting speed of any individual machine. So let's go and put this away so that we can go and showcase that. If I highlight over this, what we can do is we can go and select we'll go up to the crafting speed. So you can select this. What this does is a Lua script that's going to say, hey, tell the game to go and print the game player, so that's us, the selected crafting speed, so the selected target, which is what I'm hovering over with my mouse, and tell me the crafting speed. That outputs this really large number. Now, Lua technically clamps this to 14 decimal points, even though this actually has more precision than that. But this is good enough for our use case, and the very simple way that I find for copying this is just typing in the numbers on a number pad, copying it, and then bringing that over into our wonderful calculator that we have here. So then what we do is we paste that number in, and then we have the option to select a machine or a furnace. Those are the only 2 that are supported. A machine can also count as a chemical plant, a cryogenic plant. The only thing that the machine can't count right now as is a recycler. That is a future consideration. We'll add that in the future. So in this case, it's a furnace because furnaces behave differently than assembly machines. So we have to select that. And then what we wind up doing, and we'll just make this larger so we can watch the entirety of it. So then afterwards, what we do is we go down here and we can see that, okay, we have specified the mining drills. We select our mining productivity level, which in our case is 8,000. I will give a caveat. If you do low mining productivity levels, this calculator doesn't work well. So just a forewarning in case you're wondering, because I've packed this together to make last minute electric mining drills work. Now, the next thing that exists, is we would need to figure out now what is going to be the speed of a mining drill. Well, mining drills don't actually have a crafting speed because they don't craft, they mine. So the only thing that we can get is the speed bonus. Well, the speed bonus is also similarly very easy to wind up getting from here. We come in here, we right click on this, and we can go and, you guessed it, we can type in speed bonus. And then that will give us a value that's in here. So in this case, this is going to be 17.37999160,767. So that is the current speed bonus of this. And actually, I have, now that I'm looking at this, I have inputted the wrong speed bonus here. So great. So we will go and update that speed bonus and we'll display that. So it will accept it as long as you put the whole entire thing in there. And then cool. So now that we have this configuration set up, what we'll do, and we'll go back to full screen, we'll go ahead and click generate. So what this is now going to do is this is going to generate for us a blueprint that we can copy and paste into the game, along with also what all the machines are doing behind the scenes and what they are going to be crafting. So right now there's a bug that displays this as a machine instead of a furnace. I will fix that eventually. But this will show kind of the active time, how long it is going to be crafting for, and then when it's going to be output blocked in this case. So what we can do is we can go even further and get some more details on this. We'll see that the inserter here is going to do a pickup, another pickup, and here it's going to do the, and then it's dropping for 4 ticks, picking up for 1 tick, and you can see kind of how long this is doing this. So if we filter this now just by the inserters, let's say, that's all that I care about, and I want to specifically select the statuses. So in this case, I can actually monitor this, and then I can see that how many pickups are there, where there's going to be 6 total pickups that we are going to go out of the transitions that happen. We're picking up 6 times, which is good. That's exactly what we were expecting. So now that we have this, what we can do is we can press this little magic copy button, and then we can go back over to Factorio, and we can go and import this string. And what this does is this creates for us a wonderful little clock blueprint. So we can right click on this. You can see that what it's described as. This is a stone brick inserter clock schedule. And when we go and we take that schedule and put this in here, you're going to see that now if I go and let's say I go ahead and start the game just so that we can see some things happen. Okay, so this has told us that it's going to take 144 ticks as a wraparound condition. That's how long the clock is going to be enabled for. We don't have to think about it. And how many times does it have to repeat? Well, there's only going to be 1 input and 1 output. So there is a very simple fractional relationship with this. So we do not need to exceed this. So then the next thing that we can see is that it has specified when it's going to activate the mining drill. It figures this out based on the speed of the drill, and also it will always enable it for 1 cycle. We'll get into more details after that. So then you can see here at ratio, this is 8, but because of how fast the mining drill actually performs, 6.5 thousand per second, this only needs to be enabled for 1 tick here and then 1 tick there. And then what you're going to see here is that now this is going to very specifically say, hey, per cycle, we're going to have 6 swings. So that's check. That is the documentation portion that I need. And it also tells you what the actual item is and what the inserter ID is. That inserter ID that's right there is the exact same one that you see in the simulator. So you can see here, this is called inserter number 1, and it's telling you what it's doing. So just like I just showed a second ago, if we go now back here, the actual blueprint matches up with the simulation. So you can pretty easily diagnose and go back and forth between them. Cool, great. All right, let's actually prove that this works out. So the way that this would work is you would take your existing build and you would wind up going and hooking up all the inserters. In my case, I usually use anything is greater than 0, just so I don't have to care about the signal. But you can override it to be the exact signal that happens to get generated with the blueprint here that goes and gets created. Now, I don't go and automatically wire these up, and the reason I don't automatically wire them up in the blueprint is you may want some and you may not want some. So you can choose which ones you want. So you just pick, in this case, these 2, you just input these, great. And then all we have to really do is just connect this to this, and then this to the mining drills, because those are the 2 targets that we have. And now I can even just go ahead and delete this whole thing and start it over from scratch, which is the worst case scenario. And you can see that it picked up a couple items, and then all of a sudden it immediately just locks in to the actual clock schedule. And you can notice here as well that if we run this for a little while, we are never getting into a situation where this inserter is blocked by the items that are in front of it. Now, that's partially because of the way that I have designed this, but also mainly because of the way that the clocks are set up. And so you can see here that everything is locked and synchronized. It's 122, there's 78 in there, 122, 78. Okay. So there's the most basic example of how the actual generator works. Now you might be asking, cool, so this is a really simple example, and I can calculate this in my head, what I'm going to do to figure these out. So if you're an experienced clocker and you've done this for a while, you go, okay, this is a pretty simple ratio to figure this out, right? This is not rocket science that you've created. Well, okay, then let's go and take a much more complex example and walk through that one. So a much more complicated setup is something like this. In this scenario, what you have is you have multiple things that are going on here. You have a foundry that's crafting actual casting pipes here, and then we're going to have a direct insertion, so there's 8 ticks coming into here, and then we have back-to-back 12 tick swings that are for a total duration of 12 ticks that's going to import the items, both of them at the same time. And now this is critical because we need this assembly machine to continue to be crafting and not be output blocked for too long, right? And then finally we have now there's a multivariable problem here to keep this one stable. The second thing that needs to happen now is that this inserter needs to just in time insert items into here, and we have low automated insertion limits. I've talked about this before, but this is a very prone to desync problem that comes from when you have lower than the stack size because you're operating in an overload scenario. So you actually have to wait longer and very specifically input the items. And what this does here is it actually does a back-to-back swing of red and yellow, and then occasionally we'll do just red. And you'll see this kind of happening, these back-to-back swings and how it's deciding what to do. And then finally, what it has to decide on and figure out is, okay, how much is the maximum amount that I can actually take out of this assembly machine without it stopping? Now, the simple answer would be I can just do one at a time, but in this case, you're seeing that this actually can do back-to-back sequential swings, which is better because then we're sending less signals over the network to these individual inserters, and then they can perform a batched operation of grabbing 2 items out. Now, that's pretty complex to do and to also have it all stable. So for simplicity's sake, what I'm going to do is now I'm going to say, well, I've already figured out all the things that we needed from the last time. So I have gone and grabbed all the crafting speeds, I've typed all those out, and I know all the components that are in here. I've also modeled the belts and their inputs. So let's go ahead and showcase that. So over here, I'm going to go and import a config. So what you can export your configuration and it will go and generate a JSON file for you that you can go and copy and paste and save it for later. The other thing you can do is you can import a config. Now, the way that I've set up my actual recording software here, you're not going to see this when this shows up, but just assume that I have done this correctly. So I'm grabbing right now a JSON file. It's called Chemical Science DI Engine JSON. And you can see here automatically all these values are going to change out. So now our target is Chemical Science. We have 11 copies here. What does that mean if we have 11 copies? If we have 11 copies, we're going to have then, in this case, there are 11 unique identical copies like this. So there's going to be 11 assembly machines. And so because of how fast this crafts, I'm not too worried about this relationship being a 2-to-1 like this. So I'm just going to be modeling this side, just from here to here. That's all that we're going to be modeling in this simulation. So in this case, what I've configured then is the Chemical Science pack machine, which has 100% productivity for engine units, and 50% productivity for casting pipes, which you can see over on the right-hand side. You can see that that's what those are. So 50% engine units are at 100%. Cool. So we've set all those up. So the next thing then that we wind up doing is we scroll down here and we can set up all the inserters. So, and this is going to be coming from the assembly machine, etc. So I've modeled this scenario. I've gone and selected all the different items and configured everything. Cool. So then we configured all the belts. So we have an input here of steel and gears that are coming in, yellow and red for sulfur. And then you can see also the Chemical Science packs that are going to be going outputting onto a belt. So now that we've done all those things, we don't have any drills, so we don't have to enable them or configure them. So let's go ahead and I'll make this in full screen mode so we can see it. And then I'm going to go ahead and say generate blueprint. So what this is doing is significantly more complicated. What it is now doing is it has to do a bunch of calculations behind the scenes. One, it has to figure out how many swings can we do, and it has automatically figured out without us telling it that it can pull out 32 items or do 2 swings back to back. And we can even see that here in the detailed analysis here, where if we filter this just by the inserter state and we say the pickups, you can see here that this is going to pick up once and pick up a second time, and then it does a little bit of a buffer swing. So what is that? So what happens with that is that it detects here, and you can even see what it's doing. It detects, hey, the machine actually has 12 of Chemical Science packs to pick up. We need to grab that so that it doesn't get output blocked over this next period, and it goes and grabs that. These other two, it had exactly at the time, it had over 28, and the other scenario had 28, so it could grab both of those and then have both times it could swing with 16 items, and you can see that here, it picked up a full stack of Chemical Science plants. And then it comes in here and says, okay, well, we have 12, but I need to pick those up to prevent it actually from continuing on down here and us not having this machine continuously crafting, which is a very important thing that we need to have. So With that being said, so it figured out all those things, and then it's created kind of a range of when these different things are going to be turned on. And it has accurately identified that both these things are going to swing back to back. And what it's trying to do is maximize the amount of items that are happening in the same tick. So it has gone and created all of those and put those all together. So what we can do now is we can copy this blueprint, and we can go now back over to Factorio, and we can go and load this up. So what we'll do is we will import now this as a blueprint. And now you can see this has a more complicated setup here. So we can see here that now there's a clock. You're seeing that has 2 cycles compared to before because of the way that the ratios work out. It has identified the correct ranges and then goes and picks all these up. And in this case, it has actually gone and specified exactly when these different periods are for the pipes to get inserted as well. So what we'll do is, I've already wired this all up, but I'll just prove for demonstration purposes that this works. And then we will copy this in here and this in here. And then we can monitor by pressing F5 just when these are running. And you can see then that the output here, even if we go and delete this whole thing and re-add it back, you'll see that it eventually will get to a point where it will completely stabilize. So it just figured out a really complicated thing. And what you're seeing here too is this has 12 items that it pulled out and is holding in its current buffer. And if we go back to the simulator, you'll see that exact setup is exactly what it described. It says, hey, I need to go and pick up 12 items, just like it did this. Now at this point, you might be wondering, well, hold up, A-Buck. How on earth do you know that it needs to pick up 12 items? You have a really complicated rule engine behind the scenes, like surely you're not actually running Factorio in the browser. Well, I press this nice little simulate step function here, and then I go here and press F12 to get into the UI. Ignore the UI problems that I have. We will fix those later. If I go and press generate blueprint here, you're going to see all of a sudden that there's all these little tick timestamps that are happening. So what do these mean? Well, you can see here that a machine has 28 items, so currently this stack inserter, number 1, is going to go pick up items, and then on that same tick, it picks up 16 items. And then you're going to see here that it swings, drops items down, and then it's holding 12, 8, 4, dropping them slowly onto a belt, and then it's swinging back. And yeah, so what I've done is I've actually modeled all of the individual components that you have configured, and modeled them and reverse engineered the way the Factorio actually handles what each individual inserter and machine and crafting speed and bonus productivity and all those wonderful nice things, how that actually behaves for the machine itself, and it runs all locally here in the browser. Why did I do this? Well, one, this takes care of the observer effect. So you want to go and look at, like I was talking about before, you model the first inserter, what is it doing, and then you go and check what each inserter is doing afterwards. So the only way to simulate that process is by actually having access to Factorio, and I can't run Factorio in the browser, so I just built it all in JavaScript. Yes, I know I built it in JavaScript, and you may hate that language, but I assure you the reason I did it was because this was the whole goal in the end. The other reason that I'm doing this is because it cuts out the middleman. I don't have to do so many, there's so many things that Factorio has to do that I can simplify drastically by just making some simple calculations that we can't do because I don't have to handle all the scenarios that the actual inserters have to do in the game. And so for that reason, I can execute 3,520 ticks and 270,000 UPS. So that's why the results come back so quickly, because we can simulate it just so incredibly quickly here. So because I've modeled all those things, now we have the easy ability to do this observation effect. So to walk you through how this works, there are 3 phases. There is a prepare step. In the prepare step, what it will do, and we can just demonstrate this here and generate it. What it does in the prepare step is it waits until every machine is output full, and it staggers them. So it does every machine one at a time. So what I mean by that specifically for this setup here, what it will do is for an infinite set of items that you have daisy chained, it'll wait until this machine is completely in the output full state. It waits until this machine is completely in the output full state, and doesn't pull any of the items out until that condition is satisfied. then and only then will it insert both of these at the same time. It will then measure how high it can craft to, and then it will go and do the same thing to the next one, and will measure how high it can craft to. So in the end, when you see this here, you're going to get a very nice little snapshot at the very end of how many items were in that machine, and it prints that out here for you so you can see it. So you can see here that the chemical science was at 32 items. The engine units were currently at a total crafted of 32, and that's how many it could craft. And you can also see here for the steel pipe how often it did, and then also what its current bonus productivity and crafting progress is. And I've meticulously modeled all those wonderful things. So that's actually how it knows that, okay, this inserter we can swing 2 times because the total that it crafted is 32, and 32 divided by the stack size of that inserter is 2 swings. And so that's how it builds all the clocking and everything behind the scenes. So, and then the next phase, what it does is it warms up the simulation where it will execute for 10 times the least common multiple of the swing time for the output inserter. So 2 times how long it takes to craft, 2 times the actual amount of items that you're going to output. And it even here will list all the ratios that you have. So you can see here that it says, okay, we're going to have 2 transfers of chemical science. This is going to do half a swing of sulfur, and then advanced circuits is going to be 3/2. And so then it actually figures out, okay, well, let me look at all the denominators of all these items, and then I know that I need 2 full cycles of the number of ticks that I'm going to need to actually go and craft this. And then it does that 10 times. So it's until it's at a, quote, stable state. That way you don't have any issues when you're transitioning from an output block condition to a non. So this is just like, it simulates it 10 times that amount just so that you're at a nice starting stable state. And then it just finally, in the simulate step, what it does is it just goes and measures exactly what each of the inserters are doing. And then it creates this timeline graph that we have here. And behind the scenes, I'm doing a lot of things like I am creating automatically, and you can see here when you're in automatic mode, you can see that it is auto-generating when it should stagger and turn on and off the clocks. And it's going to try to optimize so that they're all being inserted at the same time as much as possible. And it's also going to try to buffer and stagger things so that these individual inserters are going to swing back to back as much as possible as well. And that's why we can know here at the very end that the machine has 12 of chemical science packs to pick up, and why it holds that as a buffer as the inserter itself. And that's how we can get all this beautiful, nice little graph data that we get. But this is just scratching the surface of what this tool can do. So in some scenarios, and in probably a lot of scenarios, this tool is not perfect. So you may want to go and take over the control of the inserters yourself and clock them yourself. So if you want to do that, let me go and take you through a scenario where you would want that. So in this scenario here, we have a pretty complex timing circuit to get this right. So we have a purple science setup. And the reason it's complex is because this will craft 24 items on its output before it gets blocked. And so in that scenario, that means that since these are picking up at 16, that means it's 1.5 swings per cycle. So why that's difficult is that now what I don't support in my current clocking algorithm, it's a limitation I've put in, is I don't support a 1 swing and then 2 swings afterwards. It's always a fixed cadence where they will try to run. It's an improvement we could make later, but for right now, it's a restriction I've put in. So that actually generates a really weird clocking behavior. And you'll notice that here with the default one that it actually generates, is you'll see that sometimes it just swings twice, once, and it has these little weird wake up lists where it's like waiting for something to happen. It seems pretty good, but like it still has some issues. And so it seems kind of like out of phase based on what it auto-generated. So let's go and show what it has auto-generated. So over here, over in the browser, you can see I've set up that configuration, same thing as before. And when we go and click generate on it, you'll see that it's doing some kind of weird things here. So what it's trying to do is it's trying to maximize the period where it can be turned on for, but it winds up just kind of waiting around and not doing anything in these cases, where it's just kind of like idle, trying to do something. And then it waits for a long period of time here, and then it's just idle again, just trying to go and grab some things. And it basically creates these 2 distinct periods where it's enabled. But what's odd about it is it creates these really weird little bunchings of things. So it does a whole bunch here, a whole bunch here. And what that resorts in down to is we wind up having for 80 ticks, we transfer 80 steel, and then 32 over here, 16, and then 80. And that's fine, really, because we're still transferring the amount we need, and we know it works because we see that it's actually generating the purple science that we need for the most part. But when you look at this, you're like, okay, what's actually going on? So what you can do is you can go in here and turn this on always, and that means that it will bypass the algorithm and always insert it and just do what the game would naturally do and just insert it whenever it drops below the automated insertion limit. I have videos on that if you want to know more about how that works. So when you click on this now, you can see actually what's going on behind the scenes. So per cycle of an output of purple science, it does 3 and then 2, 3 and then 2. And if you remember, I said that I don't support this kind of even, odd kind of pattern, these odd swing patterns right now in the algorithm. So what you could do now is you could say, okay, well, I know that this is enabled from 17 to 22, 33 to 38, and we could go even into the detailed view and look a little bit further, and you can see, okay, there's a big gap here where it's not doing anything. Well, I'd like to optimize it so that these are a little bit closer and these are a little bit closer. So let me go and compute that. So you could actually go into here and we could specify ourselves a clocked range. Now, what you can do now is we know that every 56 ticks that we are going to be outputting the purple science itself. It's something that I know intuitively. You can also figure it out kind of, I need to make this better for the UI, but if you take 336 divided by the least common multiplier to get one purple science output, then we know 336 divided by 6 is 56. So eventually I'll make this a little bit easier and more intuitive to use, but right now, just take my word for that. So what you can do is you can go in here and we can say, okay, I want to enable it from, I don't know, let's say tick number 20 until, and we want 3 swings, so 36, so 56 ticks. And then we'll add another one where it'll do it later. I don't know, we'll pick that in. So I'm going to pick 112. And the reason I'm picking 112 here for this range is because I want to now clock it for this whole full period. And I want to pick a range in here and a range in here. So somewhere around the tick number 80. Now I messed around with this and I already got a configuration that works. So I will go and load that. All right, so I've gone ahead and imported that. And what you can see here is that I've specified these tick ranges. So a 3 swing tick and then a 2 swing tick for 112. So when we run this now, and you can see these periods and these, like, keep in mind these kind of idle swing periods. If we generate this now you can see these nice little tight clusterings of 3s and 2s, 3s and 2s, which the algorithm doesn't really support. And when we look at this, you can actually see that now the inserters are all really nicely lined up. So what's interesting about this is you could technically take this one extra step further. And because you have the exact clock range that you're doing this, you can actually shift this a little bit to the right or shift this a little bit to the left, depending on how you wind up clocking it. So one thing, and this is purely by style points, and I'll show this in Factorio in a second, I don't want all the machines picking up at the same time. I'd actually rather have the inserters that are picking up steel, for example. I'd like those to be going and dropping the items, and this is again just pure style. I have no idea if it's better for UPS, but it just looks cool. I want them to be dropping the steel at the exact same tick that the inserter that's picking up the rails is picking them up. So that would mean I'd have to shift them over 3 ticks or so to get this to line up. And I also got to keep in mind this little buffer room that I don't need anymore. So that's something that we can do. So let me go, and I have a configuration already loaded up, and then we can actually go and do an A/B comparison of how this impacts the rest of the of this. All right, this is gonna be a little bit off center in the camera just so that I can actually get the whole thing in and it's easy to show when I'm switching tabs. But the way that this works here now is I've configured now a range, and I've gone in and I've changed the settings to be slightly offset from the other ones. And what this does now is I have just shifted it ever so slightly. So let's go into the detailed range here. And let's load this one up and go into the detailed range as well. So if we shift between these, you can actually see I have exactly shifted the period when these inserters are picking up. So this one here on the right, this is going to be picking up here exactly when this one is dropping. And this one is dropping exactly when this one picks up. And you can actually see here how this impacts kind of the rest and shifts the crafting of all of these. So it has now more distinct, although it doesn't change the number of crafts, that we have, and we can actually just filter that down a little bit more. We can see how many times we're going to have a working mode. So this is 2 times out of 4, 30 out of 60, 15, and 15. And we go over here, do the exact same thing. Let's go and turn on the working mode. So if we cycle between these two here by switching tabs, you can see that it doesn't change anything for the assembly machines. And it also doesn't change anything for the inserters down here. They have still the exact same amount of enable periods. So we'll just measure that by saying pickup ticks. So we'll go and turn that on. And you'll also notice here on the left-hand side that it actually displays a number of status events. And these are the number of transitions to that state out of all of them. So when you switch here, you'll see that nothing has changed other than us just offsetting when they actually run. So let me go and demo this now in Factorio so that you can see what these look like. So what we have now is those 3 clocks. The original one that the algorithm decided on its own, which is running right now. You're seeing that it is still perfectly doing everything just fine, but what it does is it has kind of this like staggered little weird formation. So we have a lot more and combinations here compared to these other ones where it groups them a little bit better. And you can see that then down here as well, where this is grouping. And you can see like the tick offsets are a little bit different. They both start together for the auto and the arriving at the rails together. But then when we shift it, you can wind up seeing some different timings. So this is currently running this one where it's kind of staggered and has been kind of automatically created. Let's go and copy all these settings. This is when they're going to pick up together. And we can see that this will, the reason I'm demoing this is just to show how accurate that view actually winds up being for this simulation. Let's run this for a little bit. And then we'll, so that it all synchronizes again. What you'll notice here, that is in this particular scenario here, when this is coming back and transferring, they both transfer and swing together like this. And they transfer back and swing together. Now, if we wind up changing this, and I'd say arriving at the rail together, what I'm going to do is we'll shift this over. And we'll run this for a while. Now when this happens and we get to the spot where this starts to pick up, you can see these are now delayed. And the moment that this arrives, it turns them on. And 1 tick afterwards, this picks up as this is dropping. And then they both arrive together at the machine. Does this have any UPS benefits? Probably not. Is it cool that we can do this with this? Absolutely. So that's what the tool does. So that's just an example of how you can even more fine-tune the algorithm and take manual control when it does some wonky things. So if you're wondering how can you access this tool yourself, the short answer is I'm not hosting it publicly yet because I don't think I'm quite ready to release it. This is a proof of concept video after all. This is just showing how the tool works and kind of the progress that I've made over the last 4 weeks working on this. The good news, though, for you is that you can actually access all the source code publicly. So this is all on my GitHub page where you can access it. There is the backend portion of it, and then there's also the front end that hosts the UI, and this is all under Factorio scripts. I've documented for the most part how the backend works, and you can use all the same features that you have on the front end. You just have to go and configure everything yourself in either HOCON flavor or in configuration files that has the actual file format that the UI just generates for you conveniently. Although the UI is something that I created over this last weekend just to go and demonstrate how the tool works because it was going to be a lot better than me just showing a CLI tool the entire time. So that was the reasoning for that. So the UI is definitely in a place where it could be a lot better. Anyway, with all that being said, the main users right now that I would love to target are people that are developers themselves. So, and if you are interested in contributing, I would love help. So the best places to contact me is in just creating an issue on GitHub and then talking about a pull request that you might want to go and create and on a change that you want to make to either the algorithm, which I'll be probably paying a lot more attention to, or something you want to change on the UI, which you have pretty much free reign as I'm not the most experienced front-end developer out there. So if you want to contribute, that's a good place to do it. The other really good place to go and do that is to join my Discord and in the programming channel, and you can go and that's where I'm the most active, and you can go and talk about that. Both that will be a link in the video description below, and then also this. The main reasons why I don't want to quite release it yet is because there's a lot of things that I'm currently working on. Like there's known problems right now with if you have, let's say, a recycling recipe, You technically need to actually model this as a recycler, which I'm not doing quite yet. And if you do that right now, this will bomb and will just warn you and say, hey, I tried to simulate for 1,000,000 ticks and I never got the machine to reach an output block state, which just won't happen with nutrients. So recycling in this case. So that's a limitation that exists. Another one is just I'm still working on some pretty core features in my mind. So for example, being able to, about 2 hours ago, I wound up creating a feature that supports having multiple outputs for let's say 2 engine assembly machines that are crafting components, and then figuring out all the timings for that. It's still not quite perfect, but I have tested it. It does work, but I haven't tested with a lot of different ones, so I'm not too confident on it yet. So that's kind of how I want to go about it for now. So if you are interested, you got to build it locally, but eventually the goal is to make it public so everybody can go and import this and use all these wonderful tools that we have to go and start generating, hopefully, clocks and make the barrier to entry into clocking a lot less daunting, and having just an easy tool to use it. So if you really appreciate this kind of content, I would love to earn your subscription if you like this. And otherwise, just leaving a like on the video goes a long way. I would really appreciate it. And if you have any other general feedback, just leave a comment in the video description below. I would love to hear what your thoughts are on this tool. Other than that, thank you so much for watching. My name is Nasty. Have a fantastic rest of your day.